Okay, good morning everyone. So, welcome to the final chapter before your mid-year exam. So this one is your speed of reactions. Okay, so before we begin, okay, we can take a look at the different speeds of reaction. Okay, for example, like precipitation of silver chloride. That one is very fast, instant. Okay, or otherwise combustion of petrol and oxygen. Considered moderately fast are things like calcium and water, or even browning of cut fruits. Okay, slow reaction would be like rusting. Fermentation is basically changing the sugar, okay, to ethanol okay, we should discuss in a later chapter. Okay, I think it's carboxylic acids and your alcohols, okay, in the final chapter, okay, before your O levels. All right, okay, so first important thing here, okay, that we'd like to look at is how do you measure, okay, the speeds of reaction. Okay, so there's two ways you can measure the speed of reaction. Okay, either by the amount of product, which usually is volume of gases lah for this one. Okay, volume of gases. All right, or the amount of reactant that is used up, not formed. Okay, so used up. All right, okay, so usually this one will be in the mass of reaction mixtures. Right, okay, so the volume, if you are measuring the speed of reaction in terms of the volume of gases formed over time taken, then is centimeter cube per second or centimeter cube per minute. Okay, example is over here. All right, okay, you also have the case of the one that is in terms of the mass of reaction mixture. So this kind you will see a graph that actually decreases across time, because you have gas that is escaping. All right, later on we'll take a look at the setup itself. Okay, so the units will be in terms of gram per second or gram per minute. Okay, so one is, for example, you have the volume of gas formed. The other case, you will have the mass of reaction mixture, which will actually drop across time. Okay, but if you have the volume of gas, okay, you should see increasing and finally stay constant. Right. Okay, so two ways to do it. Okay, I hope you are clear. One is on the volume of gases formed per unit time, and the other one is the mass of reaction mixture, okay, per unit time. Okay, so the speed of reaction at an instant is obtained by drawing a tangent, okay, to the curve. Okay, I hope you all know what's a tangent to a curve. That means you pick a point and then you draw a line that just cuts the point. All right, likewise, when it's a mass of reaction mixture, you also can draw such a thing. Okay, gradient to the tangent. A tangent to the curve, sorry. Okay, then after that you can calculate the speed of reaction at that instant. At that instant means at that particular time, okay, by calculating the gradient of the tangent. Okay, so this can be done by dividing the change in volume of gas, okay, by the change in time. Okay, the other way is of course by dividing the change in the mass by the change in the time. Okay, of course we also have another way, which is to calculate the average speed of reaction. Okay, so the average speed of reaction can be calculated by the total volume of gas produced or by the total mass loss of the reaction mixture over the time taken for complete reaction. All right. Okay, so now after looking at these two ways, okay, we'll look at experiments of how we can get these two kinds of graphs. Okay, so like mentioned earlier on, when you measure the speed of reaction in the lab, there's two ways. Okay, one, you can measure volume of gas at fixed time interval. The other way is the mass of the reaction mixture at fixed time interval. Okay, so there's two ways we can do this. Okay, so measuring the volume of gas produced. Okay, let's look at the first way. So basically, if we are looking at, generally the reactions that you look at are quite common ones lah, are like things like the acid metal kind, alright, the acid plus carbonate kind lah. Usually lah, those questions for O level involve this kind because they all produces gas, right? Okay, not too complicated reactions. Okay, so if the reaction give off a gas, we can find the speed of reaction by measuring volume of gas given off at regular time intervals. Okay, so what are the variables, okay, or physical quantity that you measure? Okay, is this okay, is the volume of gas, okay, usually in centimeter cube, as well as time in either seconds or minutes. Okay, and then the apparatus you use can be a gas syringe to collect and measure the volume of gas, as well as digital stopwatch. Okay. Okay, example here is like a reaction of calcium carbonate, which is your marble chips, with hydrochloric acid, okay, to give you carbon dioxide gas. So a typical setup is like this lah. Okay, so remember to draw in your stopwatch. Okay, this one remember to draw. Sometimes when we ask you all to draw a setup, people tend to forget about this stopwatch. Okay, then you just draw the gas syringe, then lift up the stopwatch. Okay, remember to draw the stopwatch. Okay, so what kind of graph you obtain out of a setup like this is that, okay, you are measuring the gas syringe is the volume, okay, of your CO2. Okay, then the stopwatch of course is the time lah. This one no need me to tell you. Okay, you should be clear. Alright, okay, so then next thing you do is, okay, you will plot the volume of carbon dioxide against time. Okay, so the gradient at any point tells you the speed of reaction. So the gradient of the tangent will always tells you the speed of reaction. Okay, so what you can see is this okay, initially down here, this line. Okay, I'm trying to draw a tangent here. Okay, wait, let me see. Okay, never mind. Trying to see whether there's a ruler. Okay, so you can draw the tangent, okay, to that point. Okay, so what you can see is this. The gradient actually gets more and more gentle. Okay, so initially, okay, in this type of scenario, okay, what happens is this. The gradient is the largest, or sometimes we use another word called steepest initially. Okay, then the speed of reaction is the highest. Okay, then next thing, okay, what you notice is that the gradient of the graph decreases. Okay, speed of reaction will decrease as well. Then eventually, okay, gradient is 0, so reaction stops because you have no more carbon dioxide produced. Okay, usually this type of scenario because all the limiting reagent has reacted Okay, limiting reagent or limiting reactant, okay, means the same thing. Okay, all the limiting reactant has reacted. Okay, the excess one of course is still there alright. Okay, so this one you should be clear after more concept. Okay, alright, so this kind of setup, if they ask you to briefly describe an experiment, here's how to describe, okay, how you do this experiment. Procedure is to basically steps to do experiments. Okay, so this one might be a bit difficult okay, but the key here is always I think the tip that I really want to share is to think of the dependent variable, okay, as well as the independent variable, the IVDV. Okay, and how to measure them. Okay, as in how to measure them, think of the apparatus. Okay, IV, DV, okay. So this kind, how to measure them, that means you think of the apparatus. Okay, to measure the independent variable, the dependent variable. Okay, so dependent variable is what you is the basically the result of experiment lah. Okay, independent variable is basically what we set at the start lah. Okay, alright. Okay, so this case, okay, they want to measure 50 centimeter cube of HCl, okay, using a measuring cylinder and transfer into an empty conical flask. Then you measure 0.5 grams of your calcium carbonate using electronic balance, and then once again transfer into that empty conical flask as shown over here. Okay, and then what you do is you stopper it, and then using a delivery tube connect it to a gas syringe. Okay, then you start the stopwatch and then measure and record the volume, okay, of your carbon dioxide. Okay, so this one is your dependent variable lah. Okay, at every minute interval. Okay, like the independent variable down here. Okay, then okay, actually no, wait, both is considered dependent variable. Yeah, dependent variable. Okay, then you got also controlled variables, CV. Think of the control variable and how to measure. The variable, okay, which means for example, okay, your experiment 150 centimeter cube of HCl, okay, measure using measuring cylinder. Then 0.5 grams of calcium carbonate, measure using electronic balance. All right. Okay, so you stop the stopwatch only when volume of the CO2 is constant for a time interval. All right. Okay. Okay, so in the end you should get like say this kind of graph. Okay, then if people ask you how do you actually calculate the average speed of reaction, you must get the total volume, okay, of the gas produced in centimeter cube okay, over a total time taken, so which in this case is 40 over like 7. Okay, so if we calculate this part out, okay, what we should get is you run a quick calculation. Okay, so you should get 5.71 okay, centimeter cube per minute. Okay, because you produce 40 centimeter cube of gas in 7 minutes. So this is the speed of reaction. Make sure you leave the final answer in 3SF, not in fraction. This is something that you should take note of. Okay, so basically average speed is done by taking a total volume of gas divided by the total time taken for the reaction to complete. So as to say okay, let me see okay, so the second way that we can set up an experiment to measure the speed of reaction is this is by measuring the change in mass. Okay, change in mass of reaction mixture in a certain time. Okay, usually it's for reaction that produces gas because then you will have a loss in mass. Okay, so the setup looks something like this. Okay, so variables is that you're going to measure. Okay, physical quantity that you're going to measure. Firstly is the mass of reaction mixtures in grams normally. Okay, that's done using an electronic balance. Then the time, okay, in either seconds or minutes using a digital stopwatch. Alright, so once again using the same kind of experiment, okay, hydrochloric acid and calcium carbonate. Okay, because the CO2 will escape okay, from the cotton wool. Then what you notice is that there will be a drop in mass okay. Once again, don't forget to draw the stopwatch this one don't forget to draw okay, so this one you have a conical flask. with a small test tube that you tie with a thread, and then you lower it into the solution, then you start lah. Okay, so this one is good in the sense that you can lower it and then start your stopwatch at the same time, compared to the previous one. The previous one, you throw the marble chip inside, then you still have to close this thing, then connect. Okay, a lot of things to do. Okay, this one somehow cut down a lot of human reaction time. Okay, so next thing what you do is plot the mass of reaction mixture against time. Okay, gradient at any point is the speed of reaction at the particular time. Okay, so typical kind of graph that you get is something like this. Okay, you will have a decreasing curve lah. All right. Okay, so what happens is gradient is the largest initially. Okay, let's say somewhere here. Okay, steepest. Then as you proceed along, okay, you notice it get less and less steep. Okay, and eventually it becomes zero. Okay, so initially it's the largest, speed of reaction highest. Then gradient decreases, speed of reaction decreases. Okay, because usually questions will ask you how the speed of reaction changes with time. Then gradient becomes zero. Okay, finally at around like 8 minutes. Okay, and then the reaction stops. Alright. Okay, so if you need the procedures, okay, that's how you say this. Okay, once again, considering, okay, what is the dependent variable, which is the mass of reaction mixtures, plus the time. Okay, and then the independent variable, okay, which is independent variable could be your, depending on what you investigate sometimes could be the particle size, could be the temperature, those kind of things. Okay, but this case there's only one there's no comparison. Okay, could be things like temperature, concentration of acid, particle size, and so on and so forth Okay, then there are quite a couple of control variables as well. Okay, so you measure 50 centimeter cube of hydrochloric acid using measuring cylinder, just like just now. Transfer into conical flask, then you place it on the electronic balance. Okay, then measure 0.5 grams of calcium carbonate, and then using another electronic balance, okay, and then transfer into small test tube with string attached. Then you lower the test tube, cover the mouth of conical flask with a cotton wool. Okay, the purpose of doing this is so that you can prevent splashing of the solution that results in unnecessary mass loss. Okay, and at the same time also allow the gas to escape. Okay, so this cotton wool got two purpose. Allow the CO2 to escape, plus prevent unnecessary mass loss. Okay, so then after that you lower, okay, into the small test tube into the acid, and then you start the stopwatch. Okay, measure and record mass of reaction mixture. Okay, you stop only when the mass of the reaction mixture is constant. Okay, so sorry, this average speed this one should change to gram per second, right, or gram per minutes. This case is in minutes. Okay, let me change all these grams per minute, right. Okay, so this case let's take a look at what's the mass loss. Here is 57.123. Okay, so the mass loss is 60 minus 57.1 over 8 minutes. Okay, so this case I can calculate the average speed of reaction by taking total mass loss over time taken. So you will be asked to find two things, either average speed or speed of reaction at that point of time. If it's speed of reaction at that point of time, you use gradient. Okay, let me run a calculation. 0.6363 grams per minute. Okay, so that's how you calculate the average rate. Sometimes you'll be asked to write down in words rather than doing calculation, okay, depending on the question. Okay, let's have a look at some practice questions with some tips that are given to you on how to answer them. Okay, so these are actually all past year O-level questions. Okay, quite a lot of questions on speed of reaction in O-levels. Actually, that is quite require you to write quite a bit, I would say. All right, so please learn, okay, how to answer some of them. Okay, like how to find speed, how do you explain how your graph show speed of reaction changes over time, those kind of things. Okay, and yeah, how do you calculate the average speed of reaction? Okay, all right, okay, let's take a look. So this one, an experiment was done to investigate how the speed of reaction changes over time. Okay, this case you are told dilute nitric acid added into a flask, and then you have excess powdered copper 2 carbonate added to the acid. So the acid is actually the limiting. Okay, that means the one that will be completely used up. Okay, so while effervescence are being produced, the gas produced was measured. Okay, so it tells you what they do, which kind, is it the mass loss kind, or is it the volume of gas kind? Okay, so the gas produced was measured using gas streams. Okay, so you're asked to sketch the graph that you will obtain from the data collected and then label both axes. Okay, so so the volume of gas, this one is your dependent variable. Okay, so this one is the volume of your CO2, okay, in centimeter cube. Okay, so you got 4 marks. Okay, 2 marks for axis label, 1 mark for curve, 1 mark for units. All right, so remember to put units are very important. Okay, you have the time in minutes. So this kind should be the increasing curve kind, then eventually tail off. All right. Okay, so there are 4 things that you need to know. Okay, one thing is to do the okay, wait. Run off. Okay, one thing is to do this, have the units in, all these units in, then axis label. Okay, and then the curve itself. All right. Okay, yeah. Okay, so this is worth 4 marks, a lot of marks actually. Okay, all right, so the next thing that we do is to explain how your graph shows that the speed of reaction changes time. Okay, my tip here is to break it down into 3 parts. All right, always have the gradient and speed at the start, gradient and speed, how it changes. All right, how it changes, and the one and use gradient then link to speed of reaction. Okay, so here is the 3 points that I must include. Okay, so I will say gradient at the start. What happens? Okay, it's the steepest, or you can just simply say largest. Okay, which means to say the speed of reaction at the start is the highest, right? Okay, so this one can be seen. Okay, over here, if I were to draw if I were to draw a tangent, okay, a tangent, okay, then eventually the tangent becomes 0, right? Okay, so what's happened is this, initially very steep, then more gentle, then becomes 0. Okay, all right. Okay, so then becomes, okay, sorry, not becomes, the gradient decreases, cancel the become, so speed of reaction also decreases. Okay, becomes less steep, if you want to say. Okay, then if finally it becomes 0. Okay, it stops because all the acid, or all the nitric acid had reacted. All right, so that's how you answer to this kind of question. Okay, so do take note, okay, of examples such as this. Okay, these are typical questions they'll get in the O level. Okay, next thing, you are asked to draw a cross when the reaction has stopped. Okay, stop means what? Means the gradient equals to 0. Gradient equals to 0. Okay, that's the final part. So I'm going to draw it like perhaps somewhere here. Alright. Okay, that's 1 mark. Okay. Can okay, then moving on. Okay, explain how would you calculate the average speed of reaction. So for this one is the total volume of gas produced or the total mass lost over the time taken for reaction. There's two ways. Okay, in this case is the volume of gas. So average speed can be calculated by dividing the total volume of carbon dioxide formed in centimeters cube, okay, by the total time taken for reaction to complete. Okay, in minutes. Alright, so you got to write this equation out in a sentence okay. Tell me is total volume of carbon dioxide gas divide by the time taken for reaction to complete. Right? Okay. Okay. Then for practice 2, okay. So you have pieces of zinc, okay, react with dilute acid to produce, okay, a gas. Okay, this reaction completes in 6 minutes. Alright, so list the measurements you would make. So now they want the measurements that you will make to determine speed of reaction. Okay, so this case, think of the independent variable, dependent variable. So you have two things to measure. Could be the volume of gas produced, okay, or the mass of reaction mixture. Okay, both ways also can in this case. They never really restrict which way. Alright, and then the dependent variable is sorry, wrong. Apologies. Okay, so dependent variable should be the volume of gas produced on the mass of reaction mixture. Okay, then independent variable, okay, could be the time taken, okay, for reaction to complete. Alright, so when you encounter this type of situation, you must think on the dependent, okay, or the independent variable. Okay, so this case it will be easier alright. Okay, so up to me okay, I'm going to choose the mass of reaction mixture. Okay, in grams. Okay, or otherwise you can choose the volume of gas produced. Okay, both ways also can for the dependent variable depending on what you choose. Volume of gas produced, okay, in centimeter cube. Okay, then for the independent variable, okay, you can total time taken, okay, for reaction to complete. Okay, then once again, you are asked to draw a graph for measurements made in part A that will show how to speed. Okay, so let's say if I want to draw the mass of reaction mixture, okay, then that will be in grams, then over the total time taken. Okay, so always remember to put in the units in minutes. Okay, it will be this kind of graph, right? The downward curve kind. Okay, if you want to put the other kind the volume of gas one also can, no issue, but unit is in centimeter cube and the time is in minutes, right? Okay, then you do something like this. Okay, wait this one actually put time, can we? Sorry. Okay, can? Alright, okay. Okay, so for part C, I say, how would you use your graph in part B, okay, to determine the speed of reaction at 3 minutes? Okay, so this kind, okay, at a particular time means you need to put a tangent, okay? So this kind you need to draw tangent to a curve at 3 minutes. Okay, then calculate gradient of tangent by taking change in volume of gas over the change in time, okay? Or otherwise, change in the mass over the change in time. Okay, all right. Okay, so what we have is this okay, so let's say at 3 minutes is here lah. Let's say okay, then you'll be drawing a tangent at 3 minutes and then finding the rise over run all right. Okay, so a tangent, okay, to the graph at 3 minutes is drawn like what I have done so far. Okay, then the gradient of this tangent okay, at 3 minutes can be calculated by taking the change in mass of the reaction mixture in grams divided by the change in time in minutes. Right? Okay, so here would be the change in time. Here would be the change in mass. Right? Okay. Then alright, okay, then I'll stop here for the first half of this chapter.